The concrete bunker sat 18 feet underground, reinforced with steel rebar according to Soviet engineering specifications that had protected command centers from Berlin to Pyongyang. Inside, North Vietnamese General Nguyen Van Tho reviewed intelligence reports while Soviet military advisors checked their watches. American B-52s had been pounding the area for weeks, but not one bomb had come close to penetrating this fortress. The thickness of the ceiling alone, 6 feet of solid concrete, could absorb a direct hit from any weapon in the American arsenal. The Soviets had done the calculations themselves. Outside, the jungle provided additional cover. Triple canopy rainforest made visual identification nearly impossible from the air, and the location 30 miles northwest of Thanh Hoa placed the bunker beyond the effective range of most tactical aircraft. American fighter bombers had to fight their way through the heaviest anti-aircraft defenses in military history just to reach this sector. Even if they found the target, conventional bombing offered maybe a 3% chance of hitting a structure this small. The general and his Soviet advisors understood probability. They understood physics. The concrete above their heads represented mathematical certainty. General Tho had earned his reputation fighting the French at Dien Bien Phu, where artillery hidden in caves had destroyed an entire airborne garrison. He applied those same principles here: concealment, depth, and overhead protection. The bunker's ventilation system drew air through filtered shafts disguised as termite mounds. Communication lines ran underground for 200 meters before surfacing. Supply trucks arrived only at night, following routes that changed weekly. American reconnaissance aircraft photographed empty jungle. The Soviet advisors had designed dozens of these command centers throughout North Vietnam, each one a miniature fortress built to withstand sustained aerial bombardment. They'd studied American tactics in Korea, where carpet bombing had reduced entire cities to rubble, but failed to eliminate hardened targets. The mathematics favored defense. A single bomb falling from 20,000 feet covered maybe 50 square meters, a pinpoint against the vastness of jungle terrain. Hitting a specific building required either incredible luck or dozens of aircraft dropping hundreds of bombs. Neither approach worked against a target this well protected. Inside the bunker, electric lights illuminated maps showing friendly positions across 3 provinces. Radio operators maintained contact with artillery batteries and supply columns. The general's staff planned next week's operations while filing clerks organized intelligence summaries in metal cabinets bolted to concrete walls. Nobody wore helmets. Nobody rushed. The routine of military bureaucracy continued undisturbed by the distant rumble of American aircraft dropping their payloads uselessly into empty jungle. The Soviets had calculated blast overpressure, penetration depth, and fragmentation patterns. They'd tested similar bunkers against their own weapons. The engineering was sound. The location was secure. The war would be won by patience and discipline, not by gambling on improbable strikes against hardened positions. General Tho signed another order and handed it to a communications officer. The date was May 23, 1972. 11 minutes later, the impossible would arrive. Weldon Word sat in his laboratory at Eglin Air Force Base in 1965, staring at a problem that had defeated engineers since the invention of the airplane. Bombs fell in ballistic arcs, slaves to gravity and wind. A pilot released ordnance at 20,000 feet, and from that moment forward, the weapon was blind. It had no eyes, no brain, no way to correct course as crosswinds pushed it off target. The Air Force had tried everything: better bomb sights, computerized release systems, even nuclear weapons large enough that accuracy didn't matter. Nothing worked against small, hardened targets. Word had a different idea. What if the bomb could see? The concept wasn't new. Germans had experimented with radio-guided bombs in World War II, but radio signals could be jammed. Word thought about light instead, specifically laser light. A laser beam could illuminate a target with concentrated energy at a specific wavelength. Sensors on a falling bomb could detect that reflected light and steer toward it. Simple in theory, brutally difficult in practice. The first problem was physics. A bomb falling at 600 miles per hour had maybe 30 seconds from release to impact. The guidance system needed to detect laser light, calculate position relative to the target, and adjust flight surfaces, all while spinning, vibrating, and experiencing forces that would crush most electronics. Word's team built prototype sensors that shattered on release. They designed control surfaces that couldn't move fast enough. They tested laser designators that lost target lock when smoke drifted through the beam. Texas Instruments won the contract to build the actual hardware in 1968. But the development process nearly killed the entire program twice. The Paveway aid system used 4 components: a laser seeker in the bomb's nose, control fins mounted on the front section, guidance electronics, and a battery pack. Total weight of the kit, just the guidance package attached to a standard Mark 82 500-pound bomb, came in at 30 pounds. The Air Force wanted 20. Engineering teams argued that physics didn't care what the Air Force wanted. Heavier guidance packages meant shorter range and slower terminal velocity. The laser seeker itself contained a 4-quadrant detector that measured reflected laser energy. When the bomb drifted left of the laser beam, the left quadrants received stronger signals. Electronics interpreted that imbalance and commanded the control fins to steer right. The system updated 100 times per second, making constant tiny corrections as the weapon fell. But laser light at 1.06 microns, the wavelength used by military designators, scattered in humid air. Vietnam's climate threatened to blind the entire concept. Test drops at Eglin revealed another nightmare. The control fins, mounted near the bomb's center of gravity for maximum steering authority, created turbulence that destabilized the weapon at certain speeds. Engineers redesigned the fin geometry 17 times. They added small vanes to manage airflow. They adjusted the angle of attack. Each modification required new test drops, new data analysis, new arguments with Air Force officers who wanted results immediately. By 1971, the Paveway thereby had achieved an 80-foot circular error probable in testing, meaning half of all bombs landed within 80 feet of the target. That represented a revolutionary improvement over conventional weapons, which measured accuracy in hundreds of yards. But 80 feet still wasn't good enough for a bunker buried under jungle. The weapon worked. Whether it would work in combat remained an open question that only real war could answer. General Nguyen Van Tho selected his command post location using Soviet doctrine refined over 2 decades of Cold War bunker construction. The site offered overhead concealment from aerial observation, road access for supply convoys, and soil composition suitable for deep excavation. Vietnamese engineers poured the concrete in 1968, following specifications that called for 6 feet of reinforced ceiling, capable of withstanding 5,000-pound conventional bombs. The bunker represented the latest evolution in hardened target design, a fortress that Soviet advisors guaranteed could survive anything short of a nuclear strike. What the general didn't account for was orbital reconnaissance. American KH-9 satellites photographed North Vietnam from 100 miles up, their cameras resolving objects as small as 2 feet across. Photo interpreters at the National Reconnaissance Office studied thousands of images, looking for patterns. Supply trucks appeared as tiny shadows on jungle roads. Antenna arrays showed up as geometric shapes against organic vegetation. The command bunker itself remained invisible under triple canopy forest, but the supporting infrastructure gave it away. Analysts noticed supply convoys converging on a specific grid coordinate northwest of Thanh Hoa. Trucks arrived at night, but infrared sensors detected their heat signatures. Communications intercepts revealed radio traffic originating from the same location. Over 3 months of observation, intelligence officers built a pattern of life analysis showing regular vehicle movements, consistent power generation, and protected communications, all indicators of a high-value command facility. They couldn't see the bunker itself, but they knew something important sat beneath those trees. The general's operational security measures actually worked against him. By restricting vehicle access to a single concealed road, he created a detectable pattern. Supply trucks traveling to nowhere attracted attention. Satellite photos showed tire tracks appearing at the forest edge, then disappearing under vegetation, then reappearing at the same spot days later. Photo interpreters marked the location as a probable headquarters facility. Intelligence summaries rated it high priority. Soviet advisors had designed the bunker's overhead protection against vertical threats, bombs falling straight down from high altitude. The 6-foot concrete ceiling could absorb tremendous kinetic energy distributed across a wide impact area. But the engineering calculations assumed conventional weapons with circular error probables measured in hundreds of feet. The Soviets had built a fortress against inaccurate bombing, never imagining that American technology would soon eliminate inaccuracy as a defensive advantage. General Tho reviewed reports in his underground office, confident in the mathematics of protection. American aircraft had dropped millions of tons of ordnance on North Vietnam without destroying a single hardened command bunker. The statistics supported continued operations from this location. Soviet engineers had certified the structure. The jungle provided concealment. Everything suggested safety. But 30 miles away, Air Force intelligence officers briefed F-4 Phantom crews on a target designated Structure 57, a suspected command facility whose exact location had been verified by multiple satellite passes. The briefing included reconnaissance photos showing the estimated bunker position, predicted anti-aircraft coverage, and approach vectors. Weapon loads called for something new. GBU-10. Paveway 2 laser-guided bombs, each one a 2,000-pound Mark 84 fitted with a guidance kit that had never been used against a target this heavily defended. The mission planning happened in air-conditioned rooms where intelligence photos covered entire walls. Nobody told General Tho that satellites had been watching his bunker for months. Nobody mentioned that American weapon technology had just eliminated the advantage of overhead protection. The general continued his work, surrounded by 6 feet of Soviet-certified concrete, while American crews calculated laser designator aim points for a structure he believed was invisible. The Paveway guidance system depended on a simple principle that proved devastatingly difficult to execute. Follow the light. A laser designator on the ground or in an aircraft illuminated the target with pulses of infrared energy at 1.06 microns, invisible to human eyes but blazingly bright to the bomb seeker head. The seeker contained a 4-quadrant gallium arsenide detector that measured reflected laser energy hitting its sensor from different angles. When the bomb drifted left of the beam's center line, quadrants on the left side registered stronger returns. Control fins responded by deflecting right, steering the weapon back toward the brightest reflected light. The physics worked perfectly in laboratory conditions. Combat introduced variables that nearly broke the entire concept. Laser light at 1.06 microns scattered in humid air. Vietnam's atmosphere, thick with moisture and smoke from ground fires, diffused the beam like fog diffusing headlights. Engineers at Texas Instruments had calculated acceptable scatter coefficients for temperate climates. Southeast Asian humidity exceeded those numbers by 40%. Early combat tests showed seeker heads losing lock when smoke drifted between the designator and target. The bomb would be tracking perfectly, then suddenly go ballistic as atmospheric interference blocked the reflected signal. The solution required increasing designator power, but higher-powered lasers generated heat that distorted the beam itself. Cooling systems added weight to aircraft-mounted designators. Ground-based units needed larger batteries. The engineering team redesigned thermal management 17 times before achieving a laser that could maintain target illumination through combat conditions without overheating its own optics. Then came the aerodynamics problem. A standard Mark 84 bomb was essentially a streamlined tube optimized for ballistic flight. Adding control fins near the nose section, necessary for guidance authority, disrupted airflow around the weapon. At certain speeds and angles of attack, the fins created vortices that caused the entire bomb to yaw unpredictably. Test drops at Eglin revealed bombs that would track perfectly for 20 seconds, then suddenly tumble as aerodynamic forces overwhelmed the control system. Texas Instruments engineers added strakes, small vanes that managed airflow over the control surfaces. They adjusted fin size, changed hinge points, and modified the nose cone geometry. Each design iteration required drop tests with high-speed cameras recording every millisecond of flight. Wind tunnel data helped, but nothing substituted for releasing a real weapon from a real aircraft at combat speeds and watching what happened. The guidance electronics presented their own challenge. Transistor circuits in 1971 weren't robust. A bomb experienced 20 Gs of acceleration at release, then vibration from supersonic airflow, then massive deceleration forces at impact. Early prototypes had circuit boards that cracked on release. Solder joints failed. Potting compounds that protected electronics in benign environments shattered under combat stress. Engineers redesigned the entire electronics package 3 times, eventually settling on a modular system where components were individually potted, then mounted on shock-absorbing frames. Battery technology became the limiting factor. The guidance system needed power for 30 seconds maximum, the typical fall time from release altitude to impact. But batteries capable of delivering sufficient current in a small package were either too heavy or too unreliable. The final design used thermal batteries that activated on release, generating power through chemical reactions triggered by the weapon's acceleration. They worked once, produced exactly what the system needed, then died. Perfect for a bomb that only had to function for half a minute. By early 1972, the Paveway 2 achieved 60-foot accuracy in combat testing. The weapon worked. Now it needed a target worth the technology. The mission briefing at Ubon Royal Thai Air Force Base began at 600 hours on May 23, 1972. Intelligence officers spread reconnaissance photos across the briefing table, black and white satellite imagery showing jungle canopy with a single notation. Structure 57, suspected command facility. The photos revealed nothing visible on the ground, just trees and shadows. But analysts had marked a precise grid coordinate based on 3 months of traffic pattern analysis. Supply trucks went in. Radio signals came out. Something important sat beneath that vegetation. Captain Lynn Highfill and his weapons systems officer studied the target coordinates. Their F-4D Phantom would carry 2 GBU-10 Paveway 2 bombs, 2,000-pounders fitted with laser guidance kits. Total weapon weight per bomb came to 2,250 pounds, which meant reduced fuel load and limited loiter time over target. The mission profile called for a single pass. Get in, designate, release, get out. No second chances. The laser designator posed its own complications. The pave knife pod mounted under the Phantom's fuselage contained targeting optics and a neodymium-doped yttrium aluminum garnet laser that pulsed at 10 Hz. The weapons systems officer would acquire the target visually through the pod's television camera, lock the laser onto the aim point, and hold designation while the bomb fell. 30 seconds of continuous laser illumination while flying through anti-aircraft fire. Fighter pilots called it hanging your ass out. Weather forecasts predicted scattered clouds at 5,000 feet with visibility of 3 miles, marginal for visual acquisition of a target buried under jungle. The weapons systems officer would need to identify a bunker that didn't show up on reconnaissance photos, using only the marked grid coordinates and whatever visual clues appeared through the targeting pod. A wrong building meant wasting 2 precision weapons on empty jungle. No pressure. The release point calculations filled an entire page. From 20,000 feet at 450 knots, the GBU-10 would take 32 seconds to impact. During that time, the Phantom had to maintain laser designation without breaking lock. Crosswinds at altitude would drift the aircraft, requiring constant corrections. The weapons officer would track the target through the paveknife pod, while the pilot maintained altitude and heading. Combat had a way of making elegant plans irrelevant, but the math at least gave them starting parameters. Anti-aircraft defenses around Thanh Hoa included 67 known gun positions and 14 surface-to-air missile sites. The mission planners marked threat rings on the navigation charts, concentric circles showing engagement envelopes for different weapon systems. The ingress route threaded between two SAM sites, counting on speed and altitude to minimize exposure. Electronic warfare aircraft would jam enemy radar, but jamming wasn't invisibility. North Vietnamese gunners had gotten very good at shooting without radar guidance. Hai-Phil's wingman would carry conventional Mark 82 bombs for suppression, essentially bait to draw anti-aircraft fire, while the lead aircraft designated the primary target. The wingman would roll in first, dropping unguided weapons near the suspected bunker location. If the North Vietnamese opened fire on the wingman, their gun positions would reveal themselves. If they held fire, the lead aircraft would have clearer airspace for designation. Either way, the wingman absorbed the initial risk. The briefing ended with timing coordinates. Wheels up at SOI 45. Target time on target, ORO 847. Weather window closed at ORO 900 when forecast clouds would obscure the area. One shot at a target they couldn't see, defended by weapons designed to kill aircraft, using a guidance system that had never struck a bunker this hardened. Hai-Phil signed the mission roster and walked to his aircraft. The F-4 Phantom crossed into North Vietnamese airspace at 8:41 hours, flying at 22,000 feet through scattered clouds that turned the jungle below into patches of green and shadow. Captain Hai-Phil's weapons systems officer activated the paveknife targeting pod, and the television display flickered to life, showing a grainy black-and-white image of terrain sliding past at 7 miles per minute. He adjusted the pod's gimbal, slewing the crosshairs toward the coordinates marked on his kneeboard card. The grid reference pointed to dense canopy with no visible structures, exactly as the reconnaissance photos had shown. 3 miles ahead, the wingman's F-4 rolled inverted and pulled through into a 45-degree dive. Conventional Mark 82 bombs tumbled away from the wings, falling toward the jungle in a pattern meant to provoke anti-aircraft response. 4 seconds later, tracers erupted from concealed gun positions, 37mm shells walking across the sky in streams of orange light. The wingman broke hard left, afterburners igniting as he clawed for altitude through a sky suddenly filled with exploding metal. Hai-Phil held his approach steady. In the rear cockpit, the weapons systems officer centered the targeting pod crosshairs on a slight discoloration in the jungle canopy. Maybe a building, maybe just different vegetation. Impossible to tell at this range. He locked the laser designator and felt the pod's tracking system engage. A small circle appeared on his display, indicating the laser was painting the target with 10 pulses per second of invisible infrared light. Each pulse lasted 14 nanoseconds. Each one bounced off whatever sat beneath that canopy and reflected back toward the sky. The weapons release computer counted down altitude and airspeed, calculating the precise millisecond when aerodynamic forces would carry the GBU-10 from aircraft to target. At 20,000 feet, the bomb had 16,000 feet of fall before the jungle canopy. Then another 18 feet to penetrate to the bunker roof. 32 seconds of guided flight during which the weapons systems officer couldn't flinch, couldn't break laser lock, couldn't let clouds drift between the pod and the target. The release tone sounded. Hai-Phil pressed the pickle button. 2,000 pounds of bomb and guidance kit dropped away from the centerline station, immediately pitching nose down as the control fins bit into the airstream. The Paveway seeker head came alive, its 4-quadrant detector scanning for reflected laser energy at 1.06 microns. The bomb found the reflected light immediately, a cone of infrared energy bouncing off the target below. and commanded the control fins to steer toward maximum signal strength. Anti-aircraft fire shifted toward High-Fill's aircraft. The Phantom shuddered as 57 millimolar shells detonated close enough to rock the airframe. High-Fill held course. In the rear seat, the weapons systems officer watched the targeting display, keeping the laser crosshairs centered on that faint discoloration in the canopy. The bomb was falling at terminal velocity now, accelerating through 600 miles per hour as gravity and aerodynamics pulled it earthward. 20 seconds after release, the GBU-10 was still tracking. Its control fins deflected microscopically, making constant corrections as crosswinds pushed the weapon off course. The guidance system responded 100 times per second, always steering toward the brightest reflected laser light. At 10 seconds before impact, the bomb penetrated the clouds that had been threatening to block designation. The seeker never lost lock. The laser beam remained steady. General Nguyen Van Tho was signing a supply requisition when 2,000 pounds of steel and high explosive punched through 6 feet of reinforced concrete at 900 feet per second. The weapon's kinetic energy alone, independent of its explosive content, exceeded anything Soviet engineers had calculated into their protection formulas. The bunker's roof shattered. The GBU-10's impact velocity hit 940 feet per second when the weapon struck concrete. At that speed, 2,000 pounds of steel casing carried kinetic energy equivalent to a fully loaded semi-truck hitting a wall at 200 miles per hour, except concentrated into a cross-sectional area of less than 1 square foot. Soviet engineers had designed the bunker roof to distribute blast force from conventional bombs across wide impact areas. They'd calculated stress loads for weapons that exploded on contact, transferring energy through expanding gas and shock waves. They'd never considered a guided weapon delivering focused kinetic penetration. The weapon's hardened nose cone punched through the first 3 feet of concrete before deceleration forces became significant. The bomb's casing, designed to survive the initial impact, compressed as layers of steel crumpled against reinforced aggregate. Rebar bent and snapped. Concrete pulverized into powder. The weapon's momentum carried it through another 2 feet of barrier material before physics finally arrested the forward motion. Then the explosive filler detonated. 945 pounds of tritonol, a mixture of TNT and aluminum powder, converted from solid to gas in less than a millisecond. The explosion generated pressure exceeding 300,000 pounds per square inch at the detonation point. That pressure wave, constrained by surrounding concrete and unable to expand spherically, channeled downward through the hole the bomb had already created. The bunker's roof didn't just crack, it fragmented. Chunks of concrete weighing hundreds of pounds blasted into the interior space, accelerated by explosive force that had nowhere else to go. The bunker's interior volume worked against its occupants. Soviet design doctrine called for central supporting pillars that would prevent progressive collapse if the roof was damaged. Those pillars, spaced every 15 feet, meant the explosion's pressure wave bounced off vertical surfaces and reinforced itself through acoustic focusing. The blast pressure that might have dissipated in an open space instead reflected multiple times, creating overpressure zones that exceeded 50 pounds per square inch, 5 times the threshold for fatal lung damage. General Nguyen Van Tho died instantly, along with 4 Soviet military advisors and 17 staff officers. The bunker's electrical system failed as the blast severed power lines. Emergency lighting activated for 3 seconds before secondary explosions from stored ammunition destroyed the battery backup. Radio equipment shattered. Filing cabinets toppled. Maps that had been spread across planning tables burst into flame from the thermal pulse. The ventilation system that had been designed to filter out chemical weapons became a conduit for overpressure. Blast waves traveled through the air shafts, emerging at distant ventilation points with enough force to scatter camouflage netting and send debris 30 feet into the surrounding jungle. North Vietnamese troops stationed 200 meters away felt the ground shake. They ran toward the bunker entrance, then stopped when they saw smoke pouring from ventilation shafts that had been hidden beneath fake termite mounds. The bunker's structural integrity collapsed over the next 40 seconds. Supporting pillars that had been cracked by the initial blast couldn't support the weight of fractured concrete above them. Progressive failure propagated through the structure as each pillar gave way and transferred load to adjacent supports. The ceiling came down in sections, burying equipment, bodies, and classified documents under tons of rubble. Above ground, Captain Highfield's F-4 Phantom was already 15 miles away, racing back toward Thai airspace with the weapons systems officer still wondering if they'd hit anything. The jungle canopy showed no visible change, no secondary explosions, no smoke plume, just trees and shadows. The after-action report would require bomb damage assessment photography, but those images wouldn't come until the next day when reconnaissance aircraft could safely overfly the area. For now, Highfield and his crew had only the certainty that the bomb had guided properly and the hope that intelligence had identified the right target. The first report reached Soviet military headquarters in Hanoi 90 minutes after the strike. A communications officer, face covered in concrete dust, had climbed out of a secondary bunker and radioed that Structure 57 had been destroyed by what appeared to be a direct hit. The message included casualty numbers. 4 Soviet advisors confirmed dead, along with a North Vietnamese general and his entire staff. Soviet officers in Hanoi immediately demanded clarification. Direct hit? On a hardened bunker? Under triple canopy concealment? The probability of such an event approached zero. Then came the damage assessment. A Soviet engineering team reached the site that evening and found the bunker's 6-foot concrete roof penetrated by a single point of impact, not cratered by near-miss explosions, not damaged by fragmentation from multiple weapons. One hole punched straight through Soviet-certified reinforced concrete, with structural failure radiating outward from that single penetration. The engineering team took measurements and photographs, then sent an urgent cable to Moscow. American aircraft had achieved precision strike capability that violated every assumption underlying Soviet bunker defense doctrine. The implications cascaded through Soviet military planning. Every hardened command post from East Germany to North Vietnam had been designed around the same mathematics: thick concrete roofs, overhead concealment, and the statistical improbability of accurate bombing. Those assumptions had survived World War II and Korea. They'd been validated by thousands of American bombing missions that had destroyed vast areas without eliminating specific hardened targets. Soviet engineers had calculated that even if American aircraft knew a bunker's exact location, conventional weapons couldn't achieve the accuracy necessary for direct hits. Now that calculation was obsolete. Moscow received detailed technical analysis within 48 hours. The weapon had struck within 10 feet of the bunker's geometric center, accuracy that suggested guidance, not luck. Soviet intelligence officers reviewed American bombing patterns from previous months and noticed a trend: an increasing number of pinpoint strikes against bridges, power plants, and storage facilities. Targets that had previously required dozens of aircraft and hundreds of bombs were now being destroyed by single aircraft dropping 1 or 2 weapons. The Americans had developed a guidance system that worked in combat conditions. Soviet military journals had mentioned laser-guided weapons as early as 1968, but the articles dismissed them as impractical for battlefield use. Laser beams scattered in atmospheric moisture. Guidance systems couldn't survive the vibration and acceleration of bomb release. Electronic components weren't reliable enough. The theoretical problem seemed insurmountable, which meant Western claims about precision weapons were probably exaggerated propaganda. Except now a Soviet-built bunker sat collapsed in the Vietnamese jungle, penetrated by a weapon that had defied those theoretical limitations. The strategic implications terrified Soviet planners. The entire defensive architecture of the Warsaw Pact depended on hardened command bunkers that could survive NATO airstrikes long enough to coordinate counterattacks. Those bunkers represented billions of rubles in construction costs and decades of engineering refinement. If American aircraft could now destroy them with single bombs, Soviet forces would lose command and control capability within hours of any war's opening. The bunker at Thanh Hoa wasn't just a tactical loss. It was proof that Soviet defensive doctrine had become obsolete overnight. Moscow ordered immediate research into countermeasures. Could laser beams be jammed? Could smoke screens block designation? Could bunkers be hardened further? Soviet engineers began testing laser scattering techniques and designing thermal aerosols that might diffuse targeting beams. But the fundamental problem remained. If Americans could guide weapons to within meters of any target they could see, no amount of concrete would guarantee protection. The age of the fortress had ended, killed by a guidance system that turned falling bombs into hunting projectiles that followed reflected light to their targets. The Paveway laser-guided bomb achieved what conventional weapons couldn't. It made accuracy routine. In Vietnam between 1972 and 1973, American aircraft dropped 28,000 laser-guided bombs with a circular error probable of 60 feet. That meant half of all weapons landed within 60 feet of their aim point, compared to conventional weapons that achieved 3% accuracy under ideal conditions. Bridges that had survived hundreds of bombing missions fell to single Paveway strikes. Power plants went dark after one aircraft pass. Storage facilities that required squadron-level attacks now disappeared under individual bombs that followed laser light through smoke and weather to strike exactly where designators pointed them. Weldon Word's concept, a bomb that could see, had transformed from laboratory theory to battlefield dominance in 7 years. The engineering problems that nearly killed the program 17 times had been solved through incremental refinement. Stronger seeker heads, redesigned control fins, thermal batteries, potted electronics that survived combat stress. Texas Instruments delivered a guidance kit that weighed 30 pounds, cost $3,000 per unit in $1972, and could be bolted onto standard bombs already in inventory. No specialized aircraft required, no exotic infrastructure. Just a laser designator, a weapon with a seeker head, and crews trained to hold target lock for 30 seconds. The strategic impact exceeded anything Air Force planners had predicted. Soviet bunker doctrine, refined since World War II, assumed that hardened targets could survive sustained aerial bombardment because accuracy remained the limiting factor. Thick concrete roofs protected against near misses. Deep burial protected against blast overpressure. Concealment made targeting difficult. Those advantages all disappeared when weapons could guide themselves to within feet of designated points. The mathematics of fortress defense collapsed when circular error probable dropped from hundreds of yards to tens of feet. NATO immediately accelerated laser-guided weapon development. The Soviet Union initiated crash programs to harden existing bunkers and develop countermeasures against laser designation. Neither response addressed the fundamental shift. Precision guidance had made static defenses vulnerable. The tactical revolution that began with Weldon Word's laboratory experiments at Eglin Air Force Base propagated through military doctrine worldwide. Wars would no longer be won by carpet bombing or artillery barrages that traded massive resource expenditure for modest accuracy. Future conflicts would feature precision strikes where individual weapons destroyed specific targets that commanders could see and designate. The Vietnam War ended in 1973, but laser-guided weapons defined every conflict that followed. Israeli aircraft used American-supplied paveways to destroy Syrian air defense systems in 1982. NATO forces employed precision weapons to dismantle Iraqi infrastructure in 1991. By 2003, GPS-guided bombs had supplemented laser guidance, achieving accuracies measured in feet rather than yards. The progression from Weldon Word's initial concept to modern precision strike capability took 40 years, but the fundamental principle remained unchanged. Guidance transforms falling ordnance from area weapons into point weapons. General Nguyen Van Tho died because he trusted engineering calculations that assumed weapons would remain inaccurate. Soviet advisors designed his bunker using mathematics that had protected fortresses since concrete and steel replaced stone and timber. Those calculations were correct for the weapons that existed in 1968. They became fatally wrong when Paveway guidance kits turned dumb bombs into guided projectiles in 1972. The revolution happened not through exotic technology, but through applied physics, seeker heads detecting reflected laser light, control fins steering toward maximum signal strength, and weapons following invisible beams to targets their crews never saw with naked eyes. Weldon Word's laboratory work at Eglin Air Force Base killed fortress warfare. The bunker that collapsed at Thanh Hoa on May 23, 1972, represented the last generation of command posts built on the assumption that overhead protection guaranteed survival. Precision guidance made that assumption obsolete, and modern warfare has never looked back.